Okay, let's do some linear approximations. So to explain the linear approximation, let's use the equation y equals square root of x. And the reason we take this equation is because this equation is hard enough so that it gets the point across, but also easy enough that we can do some calculations by hand. Now, let's pick the point of x equals 4. Well, what is y going to be? Well, we know that y is equal to the square root of x, so the square root of 4 is 2. Okay, well, if I were to tell you what is the y value when x is 9, you would tell me that's 3, and we would be done. But the problem is, what if I give you x equals 5? X equals 5. Well, now you're stuck if you don't have a calculator, because we can't do square root of 5 by hand to a very accurate degree. Well, what do we do now? Well, normally we would try to estimate by getting the slope, and we get that by delta x and delta y. Delta x is easy. What's 5 minus 4? That's 1. But what about delta y? That's square root of 5 minus 2, and we still don't know what square root of 5 is, so that doesn't help us. Well, what if the function was no longer y equals square root of x? What if we made a linear function? Couldn't then we know very easily because of the slope? So let's try to do that. Well, we know the value of y at x equals 4. So that's an easy place to start. Let's draw a linear function. And let's use that linear function to instead find what square root of 5 is. Square root of 5. Okay, well, delta x hasn't changed. Let's call that dx now. But what about delta y? Delta y is the exact change from the original position to the new position. But the new position, according to the linear approximation, has changed. Let's call that distance dy. Okay, so we're given the function y equals the square root of x. If we want to find the linear approximation, or the linear function, what can we do? Well, we have a trick, and we know that the derivative is equal to the rate of change, which is the slope at that point, at that instantaneous point. We know that dy over dx is equal to 1 over 2 root x. dy, which we're trying to find, remember, is equal to 1 over 2 root x dx. Now, if you remember using Euler's, the point of Euler's, which is basically linear approximation, was that we wanted to find some point in the future using some known value. And our known value right now is that when x is equal to 4, y is equal to 2. So let's plug that in. What do we get? dy is equal to 0.25. Are we done now? You may think that we're done. But the problem is, when we get 0.25, well, we know that the square root of 5 can't be 0.25 because 5 is larger than 4, and the square root of 4 we know is 2. So what are we missing? Well, we found the distance from the old point to the new point, which is dy, and 0.25. But we have to remember that we didn't start from 0. We started from when x is equals to 4. So we have to add that back. F of 4. What do we add? Well, we have to add back dy. And again, calling back to Euler method, how many times do we increment? We increment once per time interval, right? So how many intervals do we have? We have one interval from 5 to 4, which we know is 1. So our estimate is actually 2 plus 0.25, which is equal to 2.25. Let's generalize this formula. How can we generalize it? Well, let's call this function L of x. What is it equal to? It's equal to f of 4 plus 0.25 times 5 minus 4. But what is f of 4? Well, f of 4 is really the point that we're using to estimate f of 5. And let's just call that value a. So f of a. And what is 0.25? 0.25 is really just the derivative of f of x at x equals 4. And we define that as a. So let's say it's the f prime of a. Now, we had to multiply it by 5 minus 4, remember. What was 5? It was x. And what was 4? It was a. And remember, what we're trying to do is we're getting the number of increments that we need to increment by 0.25. So we have x minus a. Now, some questions will ask you, what is the rate of change of y as per the physics web work? Well, we actually already solved for that. We know that dy, which is the change from the original y to the new y point according to the linear approximation, is actually just equal to the f prime of x dx. And what if we want delta y? Well, delta y is basically just the exact change. And if our a value is small enough, we can say that it's pretty much our new function. So we can just say delta y is really just f of prime of a delta x. And there you have it, linear approximation.